So, good day again, class. So, here's another lesson. So, again, it's Sir Gerald. And for today, we will be actually looking into mass relationships in chemical reactions. In chemical reactions, some sort of way, you have one pure substance that will react with another pure substance that will produce what we call a product. But for today, we will be actually looking into the the matter side of chemistry, or what we call the de- the matter definition. By matter definition, and as we have defined matter, it is anything that has mass. And by mass, we will be looking into mass as it presents itself in chemical reactions. So before that, this part of the video or this part of the lecture talks about more on how we can quantify that mass relationship, or how can we put numbers into those chemical reactions. And by chemical reactions, we will be actually revisiting what we call the macro and the micro world of chemistry. And by micro world, we actually are done talking about this, talking about atoms, molecules, the protons, the ions, and how do chemical bonds work, how do ionic bonds work, covalent bonds, and something like that. And for now, in mass relationship, we will be aligning that micro world into the more macro, or the more greater in size, which we will be using the SI unit grams for our macro world, as we describe the mass relationship in chemical reactions. So in that, we should also mention what we call the atomic mass, wherein atomic mass is actually located or can be seen on your periodic table of elements, wherein atomic mass is the mass of an atom in in atomic mass units. So in that, there is actually a practical way, or there is a practicality that on having a periodic table of elements, especially when we are talking about mass relationships. So in that atomic mass units, by definition, if you look into the atomic mass of carbon, one atom of carbon 12 actually weighs 12 atomic mass units. So by definition also, if we have hydrogen 1, we have here an atomic mass unit of 1.008. And also, if we have oxygen 16, we have 16 atomic mass units. So that is our atomic mass. And using that atomic mass unit, so the average atomic mass is weighted average of all naturally occurring elements, isotopes of an element. As you may have remembered, our atoms exist in our world, having different numbers of neutrons, meaning they have different weights. So to get the numbers that are actually found in your periodic table of elements, we just need to get the weighted average, meaning to say we need to account for the percent abundance of each isotopes of each atoms. Then using statistics, get the weighted average of that weights. Therefore, having the numbers present in your periodic table of elements. For example, we have here an atomic uh, mass of 12.01 for carbon. So this 12.01 is actually the average, or the weighted average of all naturally occurring isotopes of carbon. meaning it have accounted for carbon 12, 13, and 14. Wherein, for this example, we have here, for naturally occurring carbon, we have 98%, 98.9, or 90%, 98.90% are actually carbon 12, naturally occurring carbon, and 1.10% are carbon 13. So using weighted average, so let's look into that. How do we compute for that weighted average? So we just need to, weighted average will be the percentage of the isotope, let's say carbon 12, then its weight. We just need, or its mass. Then we add that to the percentage of carbon 13. This should be carbon 12, carbon 13, then multiplied to its mass. So then just divide that by 100, or if you use decimal points, that will be your weighted average. Therefore, getting 12.01. So another example here is the computation for average atomic mass of lithium. So, for the naturally occurring lithium, we have 7.42% are actually lithium 6, which has an atomic mass unit of 6.015 atomic mass units. And we have 92%, 92.58% are lithium 7, which are 7.016 atomic mass units. So, for the computation, we have here, so he used the percentage. So he need to divide it by 100. But you can convert this 7.042, 7.42% to 0.0742, and 92 for 0.9258. So you would not be needing to divide that by 100. Therefore, having an average atomic mass, which is 6.941. And if you are to check the atomic mass presented in your periodic table of elements, that should be actually, where is that lithium? We have there 6.941. So that is how you calculate for that average atomic mass. So for beryllium, also you need to account for the present abundance of each isotopes of beryllium, get their atomic mass units, then apply weighted average. So in that, you will get 9.012. Same for boron, carbon, nitrogen, and all of the naturally occurring isotopes of each atoms or each element. Right? In that, what's the sense of that atomic mass? What is the significance of that atomic mass? So, for an atomic mass, let's introduce another concept called the mole. So, a mole is actually a unit to count number of particles. So, in that, it is somehow similar to a dozen or a pair, wherein a dozen has 12 particles or 12 eggs, and in a pair, you have two objects. So for mole is the amount of substance that contains as many elementary entities as there are atoms in exactly 12 grams of carbon 12. Meaning to say, if we are to account for 1 mole and we need to count the number of particles, we just use this number. Wherein, meaning to say, if we have here 1 mole of each element, we have 6.022137 times 10 raised to 23. May it be particles, okay, or atoms. So that is how we account for the mole. And this number actually have a name, and its name is Avogadro, or Avogadro's number, wherein it states that for every mole of any element or any molecule, there is a 6.0221367 times 10 raised to 23 particles, molecules, or atoms. Okay? So, for the molar mass, this is how we can use the average atomic mass number. So for molar mass, it is the same with saying that molar mass is the mass of 1 mole of eggs in grams. Okay, it may be 1 mole of shoes in grams, or 1 mole of marbles in grams. And specifically for our case, we'll be talking about atoms. So molar mass is actually the mass of 1 mole of atoms in 1 grams. Meaning to say, if we account for the 6.022 times 10 raised to 23 atoms for each element, the weight of that 6.022 times 10 raised to 23 atoms in grams is actually the molar mass. Okay? So, meaning to say, if we have 1 mole of carbon 12 atoms, meaning we have 6.022 times 10 raised to 23 atoms of carbon, and that is actually equivalent to 12 grams. So what is that 12 grams? 12 grams is actually equal to the atomic mass unit of carbon 12, wherein one carbon 12 atom weighs 12.00 atomic mass units, meaning to say 1 mole of carbon 12 atoms is actually equal to 12 grams of carbon 12. So that actually applies to all elements, any elements. So if we have the average atomic mass of an element, that is actually equivalent, or that is how much in grams per mole of that element. So 1 mole of lithium ions atoms, or the weight of 6.022 times 10 raised to 23 atoms of lithium, is actually 6.941 grams of lithium. Okay? So for any element, atomic mass units is actually equal to the molar mass of that element in grams. Okay? So, to provide us a better sense of mole and grams, each element can both have the same mole quantity, but they may weigh different. So as you may see here, we have here 1 mole of carbon, copper, iron, mercury, and sulfur. And as you may see here, they are in different quantities. Okay? So since mercury is uh, somehow heavier, so it accounts for a denser uh, pack of its 1 mole. So we have here, since carbon is more loose, so we have here somehow greater amounts. But if we compare the weights of this 1 mole, uh, carbon will have the least weight than sulfur, than mercury, copper, and iron. Okay. So in that, let's use that analogy of the Avogadros and the atomic mass unit and the molar mass in computation. So if we have here, just to see the dimensional analysis. So if we have here one carbon atom, and we know that one carbon atom weighs 12 atomic mass units. We also know that uh, we have 12 grams of uh, carbon for the 6.022 times 10 raised to 23 carbon 12 atoms, meaning to say we have here 1.66 times 10 raised to 24 grams per atomic unit. So the weight of one atomic mass unit is actually 1.66 times 10 raised to negative 24 grams, wherein we get that by simply canceling out the atom. So one atomic mass unit is actually equal to 1.66 times 10 raised to negative 24 grams, and 1 gram of any atom is actually 6.022 times 10 raised to 23 atomic mass units. Okay? So in that we have here this conversion, wherein if we have the mass of the elements and we multiply that mass by the molar mass, we will have the number of moles. And if we multiply the number of moles with the atomic mass, the Avogadro's number, we will have the number of atoms of an element. And if we divide the number of atoms of an element by the Avogadro's number, we will have our number of moles. And if we multiply number of moles with the molar mass, we will have here our mass of the element. So we have here some sort of dimensional analysis here. So from mass of element, we divide it by molar mass, we get number of moles. Okay? So if we have number of moles and we multiply that with the number of uh, Avogadro's number, we will have the number of atoms, then the like. So wherein here is the curly M, or the cursive M will be the molar mass in grams per mole, and Na is the Avogadro. This is the Avogadro's number. Okay? So let's try some measurements or computations. So we have here how many atoms are in 0.55 grams of potassium. Since there is no way in or there is no system wherein we can simply just multiply or divide 0.551 grams of potassium directly to uh, number of atoms, we can actually apply what we call dimensional analysis. So by dimensional analysis, let's first define the molar mass of the compound we're in, or the atom, wherein if you check your periodic table of elements, 1 mole of potassium is actually 39.10 grams of potassium. So that is the atomic mass. Then we also know that 1 mole of any element, specifically for this point of potassium, uh, eh, 1 mole of potassium have 6.022 times 10 raised to 23 atoms of potassium. So basically, we have here our given. We need to convert that into mole. So we will be using this one as our multiplier. So we have here 1 mole of potassium per uh, 39.10 grams of potassium. Okay? So in that, you can see that we can actually cancel out grams of potassium. Also, we will be using this formula to get for the number of atoms. So we have 6.022 times 10 raised to 23 atoms of potassium per 1 mole of potassium. Okay? So what is the technique? Kasi as you may see here, baliktad. Tama ba? Nabaliktad yung ating 1 mole of potassium and the atoms of potassium. So, how do we know, yeah, how do we know if we will be putting our number of atoms or Avogadro's number on the numerator and the number of moles in the denominator. So you just need to look at your outcome. So your outcome will be atoms, and you need to convert grams into atoms. So in that, we actually can look into this given as another fraction wherein there is our numerator, we have here our denominator, as you may see here, uh, numerator, denominator, these two will cancel out. And another thing, numerator, yung mole natin dito, and we have here a mole in our denominator, meaning to say that will cancel out, and we will be left out with our atoms. So here, cancel that out, then we cancel the mole, so we are left with atoms. Okay? So we have here 8.49 times 10 raised to 21 atoms. So as you may see here, the knowledge or your techniques or the skills acquired in the first part of Chem Zero, which is the scientific quotation, will be useful for this part of the lesson. Okay? So, moving on to molecular mass. So, as you may see here, we actually talked about atoms. So how about molecules? So same goes actually for the molecular mass. The only difference here in molecular mass is we will be dealing with molecules or compounds, wherein mass or molecular weight is just the sum of the atomic masses in atomic mass unit in a molecule. Meaning to say, if we have here our sulfur dioxide, okay, and sulfur dioxide actually have one sulfur and two oxygen. So we just need to add that atomic mass units. So if we have two portions or two atoms of one element, we just need to multiply it by 2. If we have 3, multiply it by 3. So we have here 32.07 for the atomic mass unit of sulfur and 16 for the atomic mass unit of oxygen. And since we have two oxygen, we need to multiply it by 2. So we have here 32.07 plus 32. So we'll have here 64.07. So the molecular mass of sulfur dioxide will be 64.07 atomic mass units. And as for our discussion earlier regarding molecular mass is similar to atomic mass units, meaning to say, molecular mass is just equal to the molar mass of our molecule. Meaning to say, 1 mole of sulfur dioxide actually has a weight of 64.07 grams. Okay? So 1 molecule of sulfur dioxide weighs 64.07 atomic mass units, meaning to say 1 mole of sulfur dioxide is 64.07 grams of sulfur dioxide. So for the computation part, let's say we have here, we need to calculate how many atoms of, or how many hydrogen atoms are there in 72.5 grams uh, methanol or C3H80 or O. Then, first we need to identify the molecular mass or molecular weight of our C3H80, which is 60 grams. And also, we need to calculate how many moles of of hydrogen are there in C3H8. O. So how do we know that? So you just look at the chemical formula, look for the hydrogen, and look for the subscript of hydrogen. Meaning to say, in 1 mole of C3H8O molecules, there are actually 8 moles of hydrogen atoms. So why do we need that? Later, you will see. So in that also we also know that 1 mole of hydrogen have 6.022 times 10 raised to 23 atoms of hydrogen via Avogadro's number, wherein 1 mole of any compound or any 1 mole of any atom or any element have 6.022 times 10 raised to 23 atoms. Okay. So first, we have here our given, which is 72.5 grams of C3H8O. We just need to convert that into moles. Okay, so using this conversion formula, where in 1 mole of that compound have 60 grams of that compound, and we need to cancel that out, that mole, because we are actually interested in getting the number of atoms of hydrogen. So cancel that 1 mole of C3 H8O, leaving us with 8 moles of hydrogen atoms. Next, we need to convert that hydrogen atoms into to number of atoms. So we have here the Avogadro's computation. And as you may see here, we can cancel out the grams. We can cancel out the moles. We can cancel out the moles of hydrogen. And we will be left with atoms, hydrogen atoms. So we have here 5.82 times 10 raised to 24 atoms of hydrogen. So that is another example of our, what we call this, dimensional analysis, wherein we use different dimensions or different conversions to compute for our uh, for the for our interest or our hydrogen atoms. So next is formula mass. Molecular mass for the molecular compounds, and formula mass for ionic compounds. So basically, the concept is the same. It is just the sum of the atomic masses in AMU in formula unit of ionic compound. So if we have here NaCl, we just need to account for the atomic mass unit of sodium, which is 22.99, and chlorine, which is 35.45 atomic mass units. So we just need to add that, and so that the formula mass of our NaCl is 58.44 atomic mass units. So for the usage of this atomic mass units, it's almost the same with the molecular and the atomic mass. So for any ionic compound, formula mass in atomic mass unit is actually equal to its molar mass. So one formula unit of NaCl is actually 58 or weighs 58.44 atomic mass units. So 1 mole of NaCl is actually 58.44 grams of NaCl. Same concept, same computations, or same additions. So in that, let's try this using this formula, mass. So what is the formula mass of calcium phosphate, or Ca3PO4 2? So we just need to calculate for one formula unit of our calcium phosphate, wherein we have here 3 calcium and we have 2 phosphate. Also, we have 8 oxygen. Sir, the formula, or the ionic formula only have P and also only have O4. So how do we get that 2 and 8? We need to distribute this number 2 to the subscripts. So the subscript of P is 1. 2 times 1 is 2. Okay. Then 2 times 4, that will be 8. So that's why it's 8. Okay. And upon calculation, the formula unit or of calcium phosphate is actually 310.18 atomic mass units. And using the concept earlier, we're in one atomic, uh, 1 mole, uh, or the atomic mass unit of any ionic compound is actually equivalent to the mass of 1 mole of that formula mass. We have here, so the formula mass of our calcium phosphate will be 1 mole of calcium phosphate is actually equivalent to 310.18 grams of calcium phosphate. Okay? So you might be wondering how do scientists or chemists identify or measure the atomic mass units of each element or each molecule. So we actually have this what we call mass spectrometer, wherein using electron beam and sample gases of your compound, you can actually get the weight of the gases. So using, if you may have remembered the line spectra, mass spectrometer actually uses line spectra, and using the fluctuations or the peaks in the graphs that is produced by the light coming from due to the electron beam, we have here we can detect how much of the isotopes of each element exists, or the natural abundance of that uh, element. Therefore, we can compute for its average atomic mass. Okay? So in that, I will be ending this part of the lecture. So I will be posting another video regarding percent percent abundance or some sort. So in that, bye bye.